I'm now going into the color differences, because these are important to judge if a color is good or too far away from a certain standard. And the color differences are always calculated sample minus standard. That's defined that way. Okay. Yeah, and if we are talking about color differences, we have here the delta. And please note the delta L star means the same as here the delta symbol L star as DL star. So that's synonymous. Okay. Okay. And as you see, I can just do this calculation sample minus standard. I can do that for L, for A, and for B. It doesn't matter. And I will show you an example. I have a certain sample here, and I have a standard, and I want to calculate the color difference here. So I have an L value. The sample is a little bit lighter than the standard. So I'm calculating 71 minus 69, and I'm getting 2.2 here, a positive value. So the sample is lighter than the standard because the number is bigger. So I can say it's brighter or lighter. If I look at the A values, I will get a 10.2 here and a 12.7 here. So when I'm calculating 10 minus 12, I get a negative value. So it's minus 2.5 here. So the sample is on the left side on the A-axis in comparison to the standard. And that means the sample is less red. So actually both values are on the right side. It could be also greener. It's greener or less red. And here for the B values, I have a 58.1 here and a 60.5 here. And when I'm making the difference here, I'm getting minus 2.4. And that means the sample is bluer or less yellow in our case, because the sample is on the left side here, more to the blue area. So these would be the differences. So then, of course, you will ask, what is an acceptable color difference for my application? And the answer is we can't give you an answer because it very much depends here on your application, on your products. So I have two extreme examples here. If you look at car paint, we have a very tight tolerances. Yeah, so it's the minimum acceptable limit. So you might set it at 0.5 or even 0.3 for the deltas. But if you look, for example, at snack food, it doesn't matter if one potato chip is a little bit darker or lighter than the other one. So we have very large tolerances and a maximum acceptable limit here. So it's really up to your company to define the limits that are okay for your product. And now there's a fourth delta, and that's very good to use because that gives the altogether difference between a standard and a sample. So if we look at the three-dimensional color space here, and we have a standard color located here and a sample color located here, I can, of course, define the DL, DB, and DA. But what is really interesting is the distance from the standard to the sample here. And that is what's specified by delta E, the total difference between sample and standard. So this length is the interesting value. And I don't know how much you remember your mathematics courses in school, but this can be calculated by the so-called Euclidean formula. Perhaps you remember it. So what I'm doing is I'm taking the square of the DL value, then the square, and adding the square of the DA value, and adding the square of the DB value. And then in the end, I'm taking the square root out of it, and that is exactly the length of this DE star symbolized by this flash here. Okay. And again, as I told you beforehand, delta E star is the same like symbol delta E star as DE star. It's all the color distance in the three-dimensional color space. And with that value, for example, I can define a tolerance. If I have a certain standard, I can set, for example, 0.5 as a tolerance. So I would have this arrow of the length 0.5 here. And this would go in all the directions as a tolerances in all the directions. And this gives, of course, a sphere. And I can now say every sample that is inside the sphere is similar to the standard, so I wouldn't see the difference. And every sample that is outside the sphere is really distinguishable from the standard. Okay, up to here, that's fine. So we have found a single number indicator for our pass and fail evaluations. But perhaps as when you are using our instruments, you know that there are other deltas, and that is because there is a significant drawback of this delta E, and that is it is not doesn't always correspond to human perception when I look at it a little bit closer. And I will give you an example for that. I have, for example, a certain standard and a certain color here, and I have a batch 1 with a quite similar color, and actually the delta E is 1, and this is derived because it's different in all 3 dimensions. So there's a little difference in L, in A, and in B, and altogether that gives a difference of delta E that is 1. But if I look at another batch, I can see I get the same delta E of 1, but actually I can really notice the difference between the standard here and the batch number 2. Why is that? This is because there's no difference in L, but a very big difference in A, for example, here. And you see that's clearly another U, and this U is very, very well perceived by the human eye. And so this is because the color space that we found by LIB is not really uniform. And there we have to look again at the human perception a little bit closer. So for human perception, some differences are more objectionable than others. So as I told you, for example, the U is most objectionable. So if the U is changing, you see it very fast, you can say. The chroma, so the saturation, is a little bit slightly yet less objectionable here. And the light is the least objectionable here. That means if a color is changing the lightness or the brightness, I don't perceive it so fast as I do for the U, for example. And now there was another experiment done. So if you give people a certain standard color and ask them to sort some other colors which are similar to that color, you will find that it's not a sphere around the standard, but it's ellipsoids. So similar color to that color here in the middle would be a little bit to the left and to the back and forth, but very much to the upper and lower part. So I have ellipsoids here, which are getting more and more narrow to the top of the L-axis. And these ellipsoids are getting more and more flattened to a more saturated color. So that would be the same perceived color in one ellipsoid always. So that would be good to have this ellipsoid as a tolerance, because then you can say every color measured in this ellipsoid is perceived as the same color as the standard. So yeah, and you can say the axes are increasing either with the lightness or with the chroma. And therefore we have some common elliptical tolerances. One is the delta E CMC. So this was defined by the Color Measurement Committee in 1984. You will find that always in our software and our instruments. And another one is the delta E 2000. This is according to the CIE again, and it's defined in the ISO standard in 2014. And so actually we are using mostly the delta E 2000, but both are good. And actually, I really would commend to use one of these and not the normal delta E star, because that one is not very much very, very near to the human perception. And for both deltas, you have an L to C ratio that can be set in the instrument or in the software. So that means lightness to chroma. So I can define the shape of the ellipsoids. And that's very much due, it depends very much on the product you have. So mostly it's set to, we mostly recommend to use 1:1 as the ratio. But for example, in textile industry, there's a tradition to use 2:1. So it depends on your products. And just to show that again a little bit more precisely to you, how the shape of the ellipses varies for different locations in the color space, we have here, it's the projection to the horizontal color plane. So you can see red, yellow, green, blue here. And you see the shapes of the ellipsoids. They're not only different from the center to the outer part, but they are also different for different use. So that means if you're adding a little bit yellow pigment to a green color, you need a lot of pigment to make it more yellow here, for example. But if you're adding yellow pigment to an orange color here, so it's a very narrow ellipse here, and you need only very few pigments to make it more yellow. So the ellipsoids are different for every location in the color space. Yeah, that's what I said here. Okay. And well, so if you now ask what values would be good for an DE 2000, and generally it's from 0.5 to 1.5 or even to 2. It depends very much on the industry it's used in. And this depends on the physical characteristics of the samples. For example, how is the surface? Is it smooth? What color is it? Is it rather uniform? Has it a texture? And all these characteristics here. And also, of course, from the end customer requirements. So is it very important that you have exactly the right color, or can it be just about the right color? And there's just some general rules for defining a tolerance. So you would choose a small tolerance for rather smooth surfaces, because there you see easily a difference in the color. And again, for rather homogeneous samples, like many colors in plastics, and for large surface, because if you have a large surface that you're measuring, you're really covering a big surface, and so you have a big average value. And you would use a large tolerance for textures and surfaces that tend to be not uniform. For naturally non-solid colors, like for example carpets or building materials, you can't really exaggerate that they are exactly the same color, for example. And for small surfaces, because you have a big deviation already, because you don't have a very big averaging of a surface. So as a summary, we can say to evaluate the color, the L star, A star, B star color space together with an elliptically shaped tolerances is a very good system, because it's intuitive, precise, and corresponding very well to human vision.